there? All right. I'm Joan Classman. I work for Intel. I talk about the Intel DPDK. Quick agenda. I'm just going to, the first few slides are kind of high level, almost marketing level slides, but they at least give you kind of some sense of how the software is organized. We have a few things about performance. And then the virtualization piece might be actually one of the more interesting pieces here. And you can either take that as you like what they're doing or you don't, but at least highlight some of the limitations of existing virtualization models that we have. All right, so from a really high level, what is the DPDK? It's basically what they call an EAL, which is basically maps the hardware registers into user space. And then on top of that, we have a whole set of libraries. And fundamentally, that's what it is. It's a map the hardware into user space, and then we have a bunch of packet libraries to do classification. We have packet libraries to do, batch transmits. And all the classification stuff is optimized for the Intel, since it's an Intel product here. It's optimized for the Intel SSE, which are the CPU optimizations. And then they have some memory mapping kind of, they use huge pages, for example. And that gives them a lot of advantage as well. I'll flip right here. And I think this is probably what I just said. Memory manager, buffer manager, queue management, flow classification, just optimizing all those things. They're all libraries. When you actually get this, you don't get like a stack or anything that you would think of like that. It's very simply just a bunch of libraries with some sample applications that run on top of it. We have, for example, as part of the published kind of source, there's a L2 forwarding application, which uses the libraries. You compile the L2 app, and you can do L2 forwarding. Similarly, there's the layer 3 forwarding, which does basically IP-based forwarding. And then there's a few other things like that they've already have there for samples. But these are really sample applications with the intent that you will modify these for your environment. They're not, per se, like supported applications that we are giving to people that are actually running them in their production environment. We expect that you'll go and tweak these and make them your own. So, one question I get is, where does all the performance come from? And it was obviously, or why is this good for performance? And it's a question I had too when I was looking at this. And here are a few of the things that they can actually do. One is they put the drive, it's all poll mode. So that helps. The other thing they do is they aggressively isolate the CPUs. So in all the documentation and the sample applications that they provide for this, you see a very one-to-one mapping of software threads to hardware queues, and all on one CPU. And they can do this because some of the environments they're looking at here are not big multi-processing, multi-threaded environments. They're looking at very targeted kind of applications for this. And to the point where they're even isolating CPUs at boot time that are going to be bound to this application so that the scheduler isn't trying to use them. The next thing we do is there's some batch packet processing going on there to do multiple packets at a time. This is something that I think we could probably do in the kernel as well. There's, just because a lot of stuff is done in user space doesn't mean it couldn't be done in kernel. It just means that we haven't got to it yet, or it hasn't been done yet. Batch packet processing might be something that we could pick up. And I know it's come up a handful of times here and there. The other one is the huge memory pages, which I just mentioned. That basically came out of some performance analysis that we had done with some tools that showed that the TLB was thrashing. By using huge pages, they reduced the thrash in the TLB. Okay. Now, the next thing is the Sse instructions. So those are the Intel streaming SIMD extensions. Basically doing vectorization for some of these tuples and things. GCC can also do this as well, so in theory you could compile your kernels with this support. And the last one there is they have some lockless queues, so all their queues are using are CIS queues. They're not really spin locking on anything. Combine that with the fact that you're pinning everything down to CPUs, and you've made a performance improvement. Here's just a kind of what an application would kind of look like. Receive a packet, reassemble it, run your flow table match. And from there, you can create a bunch of actions, ACLs. And then the KNI, which is the kernel network interface. This is an actual interface back into the kernel. Now, as soon as you start pushing packets back into the kernel, you're losing a lot of the benefit of having them in user space. So here's a quick performance numbers that they're showing. And I just put the slide in here because I'm going to say some of the challenge that they're trying to solve with this. You know, at 40 gigs, you're looking at 60 million packets per second. And then they're showing you some of the latency numbers here. L3 cache hit latency is 40 cycles. Memory read is 70 nanoseconds. So we're just trying to show that if you're trying to get line rate at 64 bytes, going from 40 gigs and then future 100 gigs, you're looking at, let's see, really short packet arrival times there, 16.8 nanoseconds and so on. And this is our test setup, and just another kind of high-level picture of what they use for their test setup. Basically, they have two systems. They use this Ixia, which is just one of these packet generators you can go buy, which will flood the link with line rate at 64 bytes. And what they're doing is they're putting in these quad ports, which are 4-port 10 gigabit NICs, putting them on a PCIe Gen 3 slots. And when they do L2 forwarding, they send them out one port and they send them back out the other port, and then they count the drop frames, or count how many frames are making it through, and then you can get your packets per second for forwarding tests. It's a pretty straightforward benchmark to do. If you could do it without the hardware test. In fact, actually, a lot of the times when I'm doing this in my setups, I don't have this fancy hardware generator there, so I just use package-in on the other Linux box and do it that way. And it works pretty well. So this is the kind of numbers that they're seeing right now. There's actually a whole slide deck of different CPUs and different platforms and the different, and it's quite extensive. In 20 minutes, we could spend half an hour just trying to interpret them. But I'm going to work with some of the guys, I think, and see if we can maybe get this published somewhere so people can actually sit there and look and see the different values for all of these things. But at a high level, they're seeing about 47, around 50 million packets per second doing L3 forwarding. And that's with a quad port using all 4 ports. And what do I have here? On the Gen 2, they're seeing about, I guess the max is 23. So these are kind of the numbers. Oh, on the right here, you have the theoretical values. So 10 gig at 64 byte, like you said, is 15 million, and then 60 million at 40 gig. And about L2 forwarding, we see about 30 million packets per second per core at 2.1 gigahertz. And then at the bottom there, we have per core numbers that they're looking at. And they can get about 30 million packets with 1 core at 64 bytes doing L2, and then layer 3, they get about 24. Obviously, as the packets get larger, they get packets per second goes down, throughput goes up. Yeah. Oh, sorry. Go ahead. Just interrupt me. So the L2 forwarding in these cases, there's only one port, so I guess they're mapping ports to back, so there's not really a table lookup. Simple answer. Look at the packet, send it out. Very simple. And since it's all done in user space and you have the rings there, it's just a matter of pushing it around. So virtualization, which is, I think, maybe the more interesting piece of this. I wanted to talk a bit about this. So what they found is they can push the stuff up into user space, into this Intel DPDK block here, which is the yellow block. And if they use shared memory, and share memory with the virtualized guest, you can get basically bare metal performance. Of course, this is a horrible idea if you don't trust your guest, right? There's no security here. You've skipped all of the stack security mechanisms. There's nothing, at some point, it's almost like running on bare metal. You're just pushing it into the VM. But the point there, I guess, is just to illustrate that it can be done, and if you have an application where you trust the application, which happens to be the case for a lot of comms applications, perhaps, then this works. And that's the bullet 4 there. Now, bullet 2 is using what they call the KNI vhost. KNI is their kernel network interface, and basically they have a device driver that will translate their internal, basically it's an SKB, it's actually a BSD style MBUF, but it translates that MBUF into an SKB and injects it into the networking stack. And by doing this, you can use existing kernel features. And this is one way to plug into a virtualization. You can use the existing stack and interfaces. You lose, the performance is basically equivalent to not doing this and using the normal kernel stack at that point. There's some slight benefit, but it's not much. And then vhostnet is a vhost extension that kind of understands their MBUF stuff, basically. There's some performance benefit there, but what they're seeing is it's mostly the performance benefit comes from, the performance bottleneck is actually in the VirtIO and not somewhere else. Question? So the question is, why not pass the PF into the VM? That can be done, but then you've effectively bound one PF to one VM, so you can't share that PF across more than one VM then. Now you could use something like SRLV, which would give you multiple virtual functions, and then you could do direct assign with virtual functions. And that works as well, and you get a lot of the performance benefits then because the VM is directly handling the packets. The problem with that is if you are a customer and you have some special software that you want to run between the VM and the physical function, you don't have any way to insert that logic anymore because you've directly assigned it to the VM. So if your Intel DPDK block there is running some library or some set of filters or something that you have written, but by using a VF or direct assigning a PF, you've lost that effectively. Yeah. Yeah. Not really. I don't believe, because what they're seeing now is then the VirtIO becomes the bottleneck, and you can process packets as fast as you'd like in the host, but we're bottlenecked at the VirtIO then. Mm-hmm. Mm-hmm. I agree, and I think the problem then is if VirtIO and the virtualization infrastructure is the bottleneck, that doesn't solve that problem, right? So you can make the host as effective as you'd like, but you still need to remove that bottleneck at the vhost VirtIO level, and maybe there's some folks here that are working in that space that have some good ideas around there. I've seen a few things, but I don't have too many details in that space. Yeah. Right. All right. So the question, just in case you didn't hear, was how much of these kind of tricks and performance improvements could actually be pushed into the kernel? I think we talked about this with someone this morning, that huge pages is something we use this, and I'm not sure how well that would work in the kernel, but maybe there's some way you could push huge pages in there. The trick, a lot of this they do at boot time, right? They say you isolate CPUs and you isolate huge memory tables at boot time. So whether or not that would be a good solution for like a driver-based solution is, or a general purpose solution, is debatable. Batch TX, I think that's come up a handful of times in different discussions, and I think that could be done. Yeah. Yeah, so that comes back to this virtual VM problem, right? As soon as we do the user copy, pull this out of the kernel, put it in user mode with this Intel DPDK, we can do this copy into the VM with shared memory without ever having to do a kernel to user space copy. So that for VMs, that's where a lot of the performance comes from. And it's how they get this to run line rate 64 bytes into a VM. And the shared memory, so they're sharing memory, so it's a zero copy effectively. Right. So yeah, and you're short.
On transmit, no copy.
Yeah.
Seems like everybody's.
Right. Yeah. The security problems are there still, right? I mean, is that what you're alluding to? There are proprietary stacks that exist that I know people are running on top of this. I'm not familiar with OnLoad. Is OnLoad just a software stack that's...
It's open onload, actually. So in
Okay.
theory, you could take open onload.
It's a user space TCP/IP stack or something? Is that... So I should...
I'd be happy if you did that, but yes,
there are proprietary TCP/IP stacks that run on top of this. And I know some people are probably doing that. I don't have direct insight to how... In the kernel space? Yeah, I think a lot of these people are, I mean, that's why this shared memory is even viable, right? You would, if you're a KVM virtualized with guests that you don't trust, you would never do this, okay? Because you would never use the shared memory model with the zero copy, right? You have to be an embedded packet crunching application of some sort. I think to get a lot of the benefits of doing the shared memory, doing the CPU aligned, and
I think that the way you're marketing it, perhaps clean interpretations of this. This should be part of the core data path, and it should be receiving packets in user space and injecting them into the kernel. And yeah, I just think that I want to hear that. But I don't think that's your guys' thought. I think that's
yeah. So that's what
the numbers you're producing are so good that people are saying, "Wow, this should be everything."
So that's the KNI piece there, is the re-injecting packets back into the kernel. And all the performance numbers aren't based on that, right? All those are based on this shared memory model where you directly copy. And KNI is one piece of it. I don't necessarily want to be hung up on it, whether it's useful or not, I guess. That's an Intel block that comes with this DPDK. It stands for Kernel Network Interface. And the point is you can take the packets from user space and dump them into the kernel networking stack. It's open source, but not upstream in the sense that it's part of the Linux kernel. Yeah. Okay, two more questions. Yeah. Okay. Right. Sure. Right. Okay. Most likely. Yeah. I'll get this last question then. Yeah, so the quick note, the other default on this is that this is an all or nothing model, unlike NetMap where you can, or I think even PFRing where you can pull certain queues out. This is pushing, there's no notion of having these packets go to user mode and then this is the main stack driver. So it's either all in user space or none of it at this time. So flow director will work with this, but not in the sense that you're thinking. All the queues are mapped into user space at this point. So you can still use flow director, but you're only, yeah.